This video is about strain gauges and pressure sensors. It corresponds to section 20.3 of Applied Analog Electronics. First, we should think about what is a strain gauge. A strain gauge, pretty obviously, is for measuring strain. And strain is defined in mechanical engineering as the change in length divided by the total length. So it's often reported in something like percent. 1% strain, so a change of 1 millimeter out of 100 millimeters, is considered a fairly large strain. So strain gauges have to measure this stretching, or if it's negative, shrinking of a physical object, usually a piece of metal or some other solid thing that can stretch or shrink a bit. They have to measure that fairly sensitively. And the usual way strain gauges are done is by changing the resistance of a piece of wire, actually a metal film, on a plastic substrate or something else that can conform to the object being strained. And it usually has a shape that looks something like this. With the wire being very long in one direction and not very long really in the other direction. In this direction you've only got a tiny little bit of wire, whereas in this direction you've got a lot of wire. And what that does is gives you a directionality to the strain gauge. Stretching it in this direction changes the resistance of the wire basically by the length of the wire, so by the amount that the wire is stretched in that direction, whereas in this opposite direction there's very little change in the length of the wire as you stretch in that direction. So strain gauges generally give you measure the strain in one direction, in one dimension. And the idea is quite simple. As you pull this thing farther apart, the wire gets longer and the resistance goes up. If you push it together a little bit, then the wire gets a little shorter and the resistance goes down. And like I say, the changes here are pretty small. Okay, so how do we end up using a strain gauge? The standard circuit is a fairly simple one. It generally consists of 4 resistors. And we have an input voltage here, which is usually a fixed voltage, and we have an output voltage here. So this circuit, incidentally, is known as a Wheatstone bridge. 2 voltage dividers, and we're looking at the difference in the output between the 2 voltage dividers. All right. Obviously, if the resistances are matched here so that the voltage on this side is the same as voltage on this side, the output is 0. But if one of these resistors is the strain gauge, then as we increase the resistance on the strain gauge, this voltage will go up. And if we decrease the resistance, that voltage will go down. And so the bridge becomes unbalanced. And the voltage that we are away from 0, so this is a differential output here, the difference that we are away from 0 is the output of the sensor. Okay, so strain gauges, fairly simple. If you've got multiple strain gauges in the system, you can do some stuff to try and increase the sensitivity of the Wheatstone bridge a little bit. Let's take a look at pressure sensors. How do they work? Pressure sensor basically consists of something with a hole in it. So we have the pressure on one side versus the other. We're going to have a thin membrane of some sort between them. And as you increase the pressure, if we increase the pressure on the bottom, we would bend this membrane upward. And if we increase the pressure on the top, we would bend the membrane downward. And what you can do is you can put a strain gauge on the surface of that membrane, and it gets stretched a little bit as you bend it. The lower side may even get compressed a little bit depending on exactly where on the membrane you're putting it. So by which surface of the membrane you're on, you can measure the stretching or shrinking of the membrane with a strain gauge. And the pressure sensors we use have something very much like the Wheatstone bridge inside. And they arrange it so that these two opposite corners here both increase together, while the other pair of corners decrease together, so that the output of the bridge, which is this differential signal here, goes up as the pressure goes up, goes down as the pressure goes down. And we're talking about the pressure difference between these two sides of the membrane. Now, depending on exactly how the package for the pressure sensor is built, that gauge, the pressure gauge here, can be one of three different types. We can have an absolute pressure sensor, which measures the pressure relative to a fixed pressure. And the way you do that is you make the thing so that the membrane is next to a closed box. The pressure inside the closed box stays roughly the same, and so, in fact, if it's a vacuum, it stays exactly the same. And so as the pressure difference between the two sides changes, that's only the pressure on the outside changing. Pressure on the inside is not changing, so it's an absolute pressure gauge. A good example of an absolute pressure gauge is a barometric pressure sensor, where you're trying to measure the atmospheric pressure, and so you want to know what it is relative to a fixed pressure. And like I say, vacuum is one that's easy to define. It's a zero pressure, but that larger pressure difference may not be desirable for the amount of strain that it puts on the membrane here. So you might very well make a box here with a fixed pressure in it that's not zero, but closer to the average pressure you expect to see. Another type of pressure sensor you see is a gauge sensor. A gauge sensor basically compares to ambient. So you're just comparing to the air around you. So you've got something, you want to measure how much more pressure you've got than the room pressure. So this is sort of the opposite of a barometric pressure meter. Barometric pressure meter is trying to measure the absolute pressure in the air. A gauge sensor is trying to measure the pressure difference relative to that pressure in the air around you. And finally, sort of the most general type is a differential sensor. A differential pressure sensor has two ports, one that goes to each side of the membrane. If you seal off one of those ports, then you've got an absolute pressure sensor. If you leave that port open to the atmosphere, then you've got a gauge pressure sensor. So differential sensors really include all the different types. It just depends on what you do with that second port. And of course you can have something where you've got the two ports going to two different places in your system to measure the difference in pressure between those two places. In fact, the pressure sensor that we use in class is a differential sensor. It has got two ports. You can connect a hose up to each one, measure the difference in pressure between those two ports. However, if you connect a hose up to just one and leave the other one open, then you've got a gauge sensor, which is generally how we'll be using it in this class, because we're mainly interested in things like blood pressure and breath pressure, and so we're interested in those relative to atmospheric pressure. We're not interested in saying, oh, the barometric pressure is high today, so the breath pressure is high. No, the breath pressure is relative to the air you're breathing normally. So the sensor in there has got a membrane like this that's machined out of silicon, and the strain gauges on the surface of it are silicon piezo resistors. So they're not metal wires, but silicon wires, and they indeed are very sensitive to small amounts of stretching. And it's set up with um, strain gauges on both sides of the membrane, some set up to increase, and on the opposite side to decrease as the membrane bends. And that is what the pressure sensor is based on, is the imbalance you get from the Wheatstone bridge no longer being perfectly balanced. And it turns out that you can make that fairly linear, and by doing some trickery with um, other resistors in your network, you can make it temperature compensated also, because resistors tend to change value with temperature also, particularly the silicon piezo resistors are temperature sensitive. Um, but you can correct for that so that you end up with a fairly uniform response independent of temperature. And the sensors we use do have that sort of thermal correction in them. Um, Other than that, there's not a lot to say about pressure sensors. They're fairly simple devices that are surprisingly useful in a lot of different lab instrumentation and biological applications.